Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders. Let's keep it in mind, year 2000, problem number 3. And I wish to say that I dedicate this video to a friend of mine, Mr 𝐿𝑒𝑠𝑧𝑒𝑘 𝐿𝑢𝑑𝑤𝑖𝑘𝑜 We say that an abelian group G has property P if for any abelian group H, its subgroup K and any homomorphism K going from this group K into G, there is a homomorphism H from this whole group H into G, satisfying the following condition: H restricted to K equals K. So this means basically that we can extend any homomorphism K from a subgroup of group H to a bigger homomorphism defined over the entire group. We wish to prove two things. Part A is simple. We wish to show that the set of non-zero rational numbers with multiplication does not have this property P. But part B, we wish to prove that Q with addition has the property P, which is much harder, as you will see. This problem is very hard, very technical. Really, it's a problem from pure mathematics studies, but in Romania it was given to 12th graders. This problem is hard, highly technical, and requires the axiom of choice, namely its equivalent version, Kuratowski-Zorn lemma. Here are my hints, or rather the outline of the proof. Part A is quite simple. For part A, consider H to be the set of integers, K be the set of even integers, and let K be defined, it takes some number of the form 2 times x and returns 2 to the power of x. Well, suppose that there is a homomorphism H which extends this function K, and consider, you should be able to do it, consider H of 1 plus 1. Well, it should be equal H of 1 times H of 1, since this is a homomorphism, which takes addition to multiplication in the other group. So this is about part A. For part B, however, we will need some new notions, or rather well-known notions, but I will present them to you. First, partial order. When we have a non-empty set, a binary relation, which I denote by this squiggly inequality line, we say that it is a partial order if x is less than or equal x. If x is less than 1 and 1 is less than z or equal z, then x is less than or equal z, and so it's transitive. And the last property, anti-symmetry, if x is in relation with y and y is in relation with x, then x and y must be equal. A relation which satisfies these three properties is called a partial order, and x with this partial order is called a partially ordered set. Another definition. When we have a partially ordered set, we say that some element x0 is maximal if, for any other element x, if this element x is greater than or equal x0, then it must be equal to x0. So if two elements can be compared, if they can be compared, then x0 is always the greater one. And by the way, what's the obvious example of partial order? Well, set inclusion is a good example of partial order. Alright, next definition. Again, we have a partially ordered set. We say that some subset A is bounded from above by an element M if every element A of this set, capital A, is less than or equal this element M. Pretty reasonable definition. Next definition. Again, we have a partially ordered set. We say that some subset C is a chain if it is linearly ordered. So in other words, every two elements can be compared. Either x is less than or equal y, or y is less than or equal x for every two elements of a chain. Yes. Chain means a subset of elements which are linearly ordered. And finally, the key to solving this problem, this well-known theorem, Kuratowski-Zorn lemma. Let X with this relation less than or equal be a partially ordered set in which every chain is bounded from above. Every chain, we suppose that we have a partially ordered set and every chain is bounded from above. Then there is a maximal element in this set X. There is a maximal element. This lemma is equivalent to the, a bit problematic for some people, axiom of choice. So we'll be touching the very foundations of mathematics, the very axioms of mathematics in this problem. All right, so after these definitions, suppose that we have some abelian group H. I will denote its operation by addition, and let K be its subset and let K be a homomorphism from the set K, subgroup K, into the subgroup of rational numbers. Define this family. Family F consists of all ordered pairs G, capital G and lowercase g, where G is a subgroup of H, but it is also a supergroup of K. G with this addition is a group. G, smaller case g, is a homomorphism, such that if restricted to K, it is equal this function K, consider right here. And I also will consider this relation on this family F. G is less than G prime G prime. I will denote it by this rectangular inclusion sign. I say that these pairs are in a relation when G is a subset of G prime and G prime restricted to G equals G. And I claim a few things about it. First, I claim that this family F with this relation is a partially ordered set. All right, this is my first claim, which I will prove. My second claim, I will show that in this family, every chain is bounded from above. And to prove it, if you wish to try it yourself, consider any chain, any non-empty chain, because for empty chain, well, every empty chain is bounded from above by something, by anything. And for this chain, consider G0 be the sum of all subgroups G, where G are in our chain, and let G0 be a mapping which takes some element of this set G0 into G of X, where X is in some subgroup in our chain, and this pair capital G, lowercase g, is in our family. I claim a few things about this construction. Well, first of all, G0 is a subgroup, which is between K and H. Moreover, G0, I claim that it is well defined, and it is a homomorphism. And moreover, G0 restricted to K equals K. Right. As this will take a while to prove it. But as an immediate corollary of this result, we have the following. As an application of Kuratowski-Zorn lemma, we will deduce that there is a maximal subgroup G contained in H and a homomorphism lowercase g from G into the set of rational numbers, satisfying that G restricted to K equals K. And my fourth claim will be that actually this maximal element G equals the whole group H. And to prove it, we will suppose to the contrary that it is not the case, that there is an H, A in H but not in G. We will consider group G prime to be the group generated by whole group G and an element A. So this, if you don't know it, this angular brackets mean the subgroup generated by some set. Moreover, G intersected with the cyclic group generated by A is again a cyclic group, well-known result from abstract algebra. And let's say that it is generated by L times A for some non-zero integer L. And we will define new function G prime. Going from this new bigger group G prime, it will take element of a form x plus ma, and it will return g of x plus m over L g of LA, where x is in group G and m is an integer. And my fifth and final claim is that G prime is a well-defined homomorphism which extends this homomorphism G, which will immediately give us a contradiction. So it's the outline. So if you wish, pause and ponder upon this problem, but it is hard, it is technical. All right, so let's go to part A. Part A is actually quick and easy. So we wish to prove that a group of non-zero rational numbers with multiplication does not have property P. How can we prove it? Well, let's consider, as I suggested, H to be the set of integers, K to be the set of even integers, and we define K, which takes 2x to 2 to the power of x. Obviously, H is a group. Obviously, K is a subgroup, because if we take two even numbers, again, after addition, we get an even number. If we take an even number, the opposite of it is also even. And 0 is, of course, an even number. But now, let's suppose that it is possible to extend this homomorphism K to a bigger homomorphism, H, defined on the entire set of integers. Now, since we suppose that it is a homomorphism, this should be the case. H of 1 plus 1 should be H of 1 times H of 1. Yes, it takes operation in one group to the operation in the other group. But here is the problem. H of 1 plus 1 is H of 2. And H of 2, let's go back to our definition, H of 2 is the same as K of 2, because it extends our function. And what is K of 2? It's 2 to the power of 1. So it's 2. And H of 1 times H of 1, well, obviously it's H of 1 squared. And now here comes the problem. Since H of 1 squared equals 2, it must be the case that H of 1 equals plus or minus square root of 2. But here's the problem. This number is not rational. It's not rational. So we get an immediate contradiction. So we get an immediate contradiction. It is not possible to extend this homomorphism beyond the set of even integers. So part A is done. All right, here we have our definitions. I will pass them. Yes, for part B, we are supposing that H with addition is an abelian group and K is its subgroup, and we have this homomorphism K. I have defined my family as I have suggested, and I have defined this relation between pairs of elements of our family. I claim that this is a partially ordered set. Partially ordered set. Let's prove it. Proof. We have to prove a few things, 3 things in total. First thing is that is every pair in relation with each other, with itself rather? Well, it is, because notice that obviously, or maybe let's write it in white. Obviously, G is a subset of G, and any function G restricted to G is itself. So any pair G is in relation with itself. All right. Second thing, so let's suppose that we have G is in relation with G prime, and G prime is in relation with G double prime. What then? Well, notice that then we have the following 2 inclusions, and also I will have to move. Give me a minute, I have to put this part a bit lower, some space. It is. All right. Then, well, since we have these 2 relations, well, G is a subset of G prime, and G prime is a subset of G double prime. So G is a subset of G double prime. It's one thing. But second thing, well, G double prime restricted to G prime equals G prime, and G prime restricted to G is G. Now, what happens if I restrict G double prime just to G? Well, notice that then G double prime restricted to G, since G is a subset of G prime, it is the same as G prime restricted to G, but G prime restricted to G is G. So G is a subset of G space. So G is in relation with G double prime. So our relation is transitive. And moreover, let's suppose that G is in relation with G prime, and let's suppose that it is also the other way around. Well, then, what do we have then? Notice that since G is a subset of G prime, but also G prime is a subset of G. So then G equals G prime. So our domains of our functions are the same. And moreover, well, notice that G restricted to G prime is G prime, but G prime is also entire domain G. So G equals G prime. So we have equality of these two pairs. So it proves that our relation is a partial order on the family F. It proves our first claim. Second claim, harder one. I claim that every chain is bounded from above in our family. Proof. Let C be a non-empty chain, because for empty chains it's trivially true. Be a non-empty chain. I define this set G0 to be sum of all subgroups G, where G is in our chain, and G0 is this mapping right here. My subclaim is that it is a group between K and H, and that G0 is actually well-defined homomorphism, and that G0 restricted to K is again K. All of that means that G0 is in our chain. Not in chain, but in our family F. Let's prove claim number 3. Proof. Let's go one by one. Well, let's start with this. Notice that since K is a subset of G and G is a subset of H, for every G in our chain, we have, or even in our entire family, we have, well, obviously, sum of all elements G is in our chain. It is obviously, again, it has K as a subset, and it is included in H. Well, all right. Is it a group? Let's check it. To check that it is a group, let's do the following. First, notice that 1 is in any G for any G in our chain. or rather not 0 because I denote my operation as plus, so 0 is in this group. So it is since this chain is non-empty, it is also included here, which is actually G0 by definition. All right, now let's suppose let X belong to G0. I wish to show that its inverse is also in G0. Well, then this element X is actually in some group G or some G in our chain. So, which means that X inverse is also in G, because G is a subgroup. i.e., so it is in our group G, so it is also in our entire union of groups. Now, next part, let X and Y be two elements of our set G0. Well, notice that then X is in some element G, Y is in some group G prime for some G and G prime, which are in our chain. All right, now it's time to use the fact that it is linearly ordered. Since this chain C is linearly ordered, is a linearly ordered set, we may assume, without loss of generality, we may assume that, well, in particular, that, for example, G is in relation with G prime. Well, notice that then G is a subset of G prime, so both X and Y are in our group G prime. Notice that then their product, or their sum rather, and also, sorry, one more thing. I denote my operation by plus, so it's better to write inverse element as minus x, not x to the minus first power. Sorry about that. Then x plus y is again in our group G prime, so it is also in the entire union of these groups, which proves, that G0 with addition is a group. And it is included, it is somewhere between K and H. So I have proved the first part of my claim. Second part, G0 is well-defined homomorphism. Let's go back to G0. G0 maps x's to G of x. Oh, maybe let's rewrite it right here. G takes element x and maps it to G of x in our set of rational numbers, where x is in G and G is in our chain. The problem is there are multiple ways, because any element x can be in multiple elements of our chain. The problem may arise, is the value of this function the same for every G? Let's verify it. So suppose that this element x is in G, it is also in G prime. We wish to show that G of x, where G and G prime is in our chain. We wish to prove that g of x is actually the same as g prime of x. Again, we will use the fact that our chain is linearly ordered. Since C with this relation is a linearly ordered set, we may assume that, for example, that pair G is in relation with G prime. Notice that then G is a subset of G prime, and G prime restricted to G equals G. Alright, but now let's remember that X is in G. In particular, well, G of X, it is both in X and in G and in G prime, is the same as G prime of X, which proves that our function G, or rather G0, sorry about that, G0 is well defined. It is well defined. Alright, but is it a homomorphism? Let's prove it. So now we have a few things to do. First, what is G0 of 0? Well, G0 of 0 is G of 0, and it is 0 because well, 0 is in any group G, or any G in our chain. Alright, so the neutral element is mapped to itself. And what about the sum of two elements? So now let X and Y be two elements of G0. Again, the same trick. Then X is in G, Y is in G prime, where G is in our chain, and G prime is in our chain. Once again, it is linearly ordered. We may assume that, well, that G is in relation with G prime. So G is a subset of G prime, and G prime restricted to G equals G. Notice that then also I need to give me a break because I need to put this a little bit lower because I'm running out of space. But notice that then we have the following. What is G0? G0 at X plus Y. G0 at X plus Y, well, let's take a look. Both elements X and Y are in G prime, so it can be written as G prime of X plus Y. But G prime of X plus Y, G prime is assumed to be a homomorphism, so it's G prime of X plus G prime of Y, which is actually, once again, G0 of X plus G0 of Y. i.e., our function G0 is a homomorphism. i.e., G0 is a homomorphism. And last part to be demonstrated is that let X be an element of this set K. Well, notice that then K is a subset of G for any G in our chain. So, well, G0 of X equals G of X, but G of X is assumed to extend function K. So it is K of X, which, if we go back to our claim, well, I have demonstrated that it is a well-defined function, I have. I have demonstrated that it is a homomorphism. I have. And it extends K. So this means that this element G0 is an upper bound, of our chain. Yes. Yeah, why is that? Because G, of course, is a subset of the union of all its elements. And also, obviously, G0 extends every function G in our chain, which proves our claim. Actually, it was a claim and it was a subclaim, so both claim and subclaim are demonstrated. Corollary: there is a maximal subgroup of our group H, and there is a homomorphism G extended K, extending homomorphism K. It follows from the Kuratowski-Zorn lemma. All right. Now, fourth claim. I claim that this subgroup, this maximal subgroup G, equals the whole group H. If I show that, this is the end of the proof. Suppose to the contrary that there is an element A which is in H but which is not in G, and I define these new things. G prime, let it be by definition the group generated by G and this element A, and it is well known fact that for abelian group this set consists of elements of the form x plus ma, where x is an element of G and m is an integer. Alright, moreover, G intersected with cyclic group generated by A, again, it's a subgroup of A, but any subgroup of cyclic group is again a cyclic group, so it is generated by some element of this group, and every element of this group can be written as L times A, where L is some non-zero integer. Well, non-zero because we are supposing that, let's go back, so we are supposing that A is not in G, so it's not zero, so it can't be zero. And I define new function G prime, which takes an element of the form x plus ma and maps it to G of x plus m over L, G of LA, where x is from group G and m is an integer. Well, I claim that G prime is a well-defined homomorphism which extends G. Proof. Let's prove it. Let's prove it. Well, what do we have to do? Well, first of all, is it well defined? Because many elements of G prime can be written in this form. So suppose, let's start, suppose first that x plus ma equals y plus n na, or some x and y in our group G and integers m and n. But notice now the following. We can write it as x minus y equals n minus m times a. And now let's see the following. This element right here is of course in G, because x and y are from G, while this element is of course in the group generated by A. Alright, so since they are equal, both of them are in the intersection. Of these two groups. And remember that we assume that this intersection is generated by LA. We can write therefore that x minus y equals KLA, and the same can be said about n minus m times a. It can be also written as KLA for some integer k. All right. And now I wish to deduce something, because let's see, y can be written as x minus k al. That's one thing, but also n can be written after division by a by taking inverse, or by putting everything on one side. It can be deduced that n equals m plus k times l. N equals m plus kl. Yes. All right. Or rather, maybe, you know what, it is not exactly the case, but we can write that n minus m minus kl times a can be written 0. Maybe let's write it in this way, because this division is not really possible. All right, and now let's compare. Let's now compare this element. Let's compare this and let's compare that. We should demonstrate that these two things are actually equal. Well, notice the following. Let's write this. G of y, maybe let's write it in different color. G of y plus n over L G of LA. It can be written, what is G of y? Well, y is x minus k LA, and n, and here we can write n over L G of LA. All right? Now, G of that can be written as G of x minus k minus k times G of LA plus n over L G of LA. All right, so we have G of x, and now here we can write it as n minus kl over L G of LA, G of LA. All right, but notice that n minus kl over L, it is m over L G of LA. All right, maybe let's spend a while on demonstrating this equality. Well, notice that n minus kl minus m over L G of LA, it can be written, we can actually take this inside because it's a homomorphism. So it can be written as 1 over L, because it's just a division in rational numbers. G of L n minus kl minus m times a. But remember, we have demonstrated that n minus m minus kl times a is 0. This part right here is 0. So we have 1 over L times g of 0, but g of 0 is 0, so it's again 0. So this crucial equality, that this equals that, has been demonstrated, which means that our function is indeed well-defined. It's well-defined. All right, maybe let's write it. All of that implies that G is well-defined, or G prime is well-defined. It is well-defined. Yes, it is. All right, but is it a homomorphism? Well, let's take a look. What is G prime of 0? G prime of 0 Well, notice that it can be written as g prime of 0 plus 0a. And now, by our definition, it is g of 0 plus 0 over L g of LA. But again, g of 0 is 0, and here we have 0, so it is just 0 plus 0, which is 0. All right. And now, let x, y be in our group G. Let m and n be any integers. Notice that then we have the following: g prime of x plus al, g x plus ma plus y plus na. We can group it in the following way: x plus y plus m plus n times a. Now, using our definition, it's the same as g of x plus y plus m plus n over L g prime, or g rather, LA. All right. But now g is a homomorphism, so it's g of x. I can write plus m over L g of LA. Then I can write g of y n over L g of LA. And this can be written, this first part, it is exactly g prime of x plus ma. And the second part is exactly g prime of y plus na, which proves that our function g prime is a homomorphism. It is a homomorphism. Right? All right, and what next? What next? And so we have demonstrated that it is well-defined homomorphism, but does it extend our function g? Well, let's see. Let's see. If x is in our group G, then notice that g prime of x is the same as g prime of x plus 0a, so it is g of x plus 0 over L g of LA. So it is g of x. So g prime restricted to g equals g. And this means, this proves our claim, or it rather proves that, maybe let's write it, since g is a subset of g prime, and g prime restricted to g equals g, we have demonstrated that g is in relation with g prime. But remember that our set G was supposed to be maximal. G was supposed to be maximal. So it must be the case that we have actually equality right here. But now we have a problem, because recall that A was assumed to be not in our group G. But A was assumed to be in H, but not in our group G. So G cannot be equal G prime. Contradiction. We have reached a contradiction right here, which means that all of that means that actually G equals H. So we have a homomorphism G going from G to the set of rational numbers satisfying G restricted to K equals K, which closes the proof, the entire proof of our. It was exactly our goal. A hard proof, very technical, I'd say. Very hard for 12th graders, but it is what it is. Few remarks before we go. First remark. Well, what was different about Q with addition and Q star with multiplication? Well, the crucial difference was exactly here. Because since we have addition, here we have just a normal fraction, m over L. Well, if we multiply any rational number by m over L, we again get a rational number. If our operation wouldn't be addition but multiplication instead, in this place right here, instead of m over L, g of LA, we would have g of a to the power of L to the power m over L. And now problems appear, because a rational number raised to a rational exponent need not be rational. It can be irrational. We have seen an example. For example, 2 to the power 1/2. 2 to the power 1/2 is square root of 2. It's irrational. So here is the key difference between point A and point B of our problem. So it was a first remark. Second remark. Well, this proof is based on Kuratowski-Zorn lemma. It is Kuratowski-Zorn lemma. If you don't know anything about it, it's an equivalent formulation of the axiom of choice. The axiom of choice is one of the axioms of set theory, very foundations of mathematics. And this axiom of choice is actually nowadays is more or less accepted by mathematical community, but it leads to various strange results in mathematics. Doing mathematics without the axiom of choice is hard. Many useful things cannot be proved without the axiom of choice. But on the other hand, assuming the axiom of choice also leads to strange results. For example, Banach paradox of sphere decomposition. You can read about it on Wikipedia or somewhere. I doubt that there is a version of this proof without using the axiom of choice. I really doubt it. I think that some version, maybe some weaker version of the axiom of choice is needed. Maybe some weaker version is sufficient, but I think that some version of the axiom of choice is required to complete this proof. Who knows, maybe it is also equivalent to the axiom of choice. If you are doing some research in pure mathematics, it may be a worth topic for you to investigate. Maybe this statement is equivalent to the very axiom of choice. I don't know. I simply don't know. And the last thing, well, since this solution is very hard for 12th graders, I tried to find an official solution published by the Romanian Mathematical Society. And I have found one. I have found an actual book which contained, published in Romania with solutions to the problems. And basically, the entire proof is just like that, except from one part. The authors of this book, I will leave the reference to this book in the video description. They say that the existence of this maximal group G is obvious. It's by no means obvious. By no means it is obvious. It's not. It requires Kuratowski-Zorn lemma. If something requires Kuratowski-Zorn lemma, it is by no way, it's no way obvious. Sorry, it isn't. So actually, I'd say that there was a gaping hole, a gap in the reasoning of the authors. And last thing, I wonder if some participant of this Olympiad actually managed to solve this problem. I'm really curious. We will probably never know, but who knows? So yes, thank you very much for watching. I hope that you've managed to stick with me to the end. Probably, maybe you did. And I wish you luck on your mathematical studies and so on, and have a nice day and see you soon. Goodbye.